Okay, tachometers. This is some work that I did a long time ago, long time ago. In fact, I realised it's almost 40 years. Surprisingly, some of the techniques are still, and chips are still quite relevant, and in other areas they've been somewhat obsoleted and supplanted. However, I had a job at GMH, and we're in the technical centres, which is the department that's designing and developing the cars. So I was in one of the support groups, basically looking after people who developed the designs of the engines, of their bodies, and that sort of, and the gear train and all that sort of stuff, and tested them. So we're in an electronics group, not for the electronics of the car, but for the electronics, and fairly sophisticated electronics, for the measurement systems are testing the car for what they call performance, which was what sort of torque it would develop, what sort of speeds it would go to, and also durability, trying to shake the things apart and see if they last, that sort of stuff. So that was all the job of the engineering department. And one of the first jobs that I was given was to try and develop and help with the getting a decent tachometer to measure the engine speed. So where are we? Here. Now, I'm just going to give a little, just a brief overview of what I'm intending to talk. This could take a while, so I'm suggesting we have a break for coffee and stuff. So what I was intending to go through is a very quick primer for on car engines for people who are not familiar with them, and then into the car ignition system, and then an overview of a tachometer, which is for measuring the revs per minute of a shaft, crankshaft in the case of a car, and look at the different types of pickup that are how you pick up the signals. Also going to get into some electromagnetic compatibility and shielding and some of those sorts of issues, because the car is one challenging environment electronically. It is possible to get it to work well, and there are a lot of people who don't know how, including car manufacturers. Look at some of the waveforms that come out of the ignition system, because the taking signals from the ignition system is usually the preferred way of doing it, or it depends on the circumstance, but that was certainly the tachometer that I was trying to develop, although I did get involved in other ones where you're picking up magnetic signals from blips on shafts and that sort of stuff. But that takes a lot more work, whereas we're talking about portable tachometers here. I, with one of my colleagues, wrote a report on evaluating a bunch of commercial tachometers that were supposed to be doing the same job. Look at the power supply, and that perhaps we'll have the coffee break. And then I'll in the second half I'll get into actually getting into the details of what we developed. So I'll give you an overview of that, and by far and away the hardest part of it was having a complex variable signal input, which was highly subject to interference and all that sort of stuff, to reliably give one pulse per spark. And it's mighty hard to do. We recently got it leaked. There are an awful lot of tachometers in the field that don't, and so we used the stuff that we developed for not only for portable tachometers but also for instrumentation and the dynamometers and that sort of stuff. So there's the pickup and the pulse shaper, which is the bit that's by far and away the hardest, and usually the thing that most automotive tachometers don't do very well over. And then there's a frequency to voltage converter and filter and the output display, and that's fairly relatively straightforward. And then I'll finish off with a few sort of thoughts on how I would do it different in modern days and what things are the same and what things have changed. So, if that's okay and we're not sort of planning on any other activity for the night except for the coffee, so let's get into it. So I'm not going to assume, or a very brief primer on engines for those who are not terribly familiar with them. So the engine of a car, the centre bit is what's known as the block, and so this is an exploded view of it. And then there's a head, the so-called cylinder head at the top. So it's bolted down, so that gap doesn't appear. That's part of the explosion, if you like. So you've got the cylinders, the holes in this great metal block, and pistons that go up and down. And when there's an explosion from a spark plug up the top, the combustion chamber here, it pushes the piston down, and that linear motion up and down is transferred by the crankshaft at the bottom into circular motion. So I've got found a couple of GIFs out on the web. So this is one of them that illustrates how those pistons going up and down. So the dark grey bits here are the metal. The dark grey bits are the metal, and so it's going in a confined space with a piston going up and down, and you can see the spark plug every now and then exploding the mixture. And so you've got valves there. The blue valves are letting in the fuel and air mixture. Spark plug sparks it, and then the red coloured valve there is the exhaust valve and lets the gases out. And most importantly, we've got the crankshaft at the bottom, where the up and down movement of the pistons is transferred to a rotary motion. And the aim of the whole game is for us to measure the rotational speed, revs per minute, of that crankshaft. I've got another GIF of it somewhere. No, it's disappeared. Oh well. Oh, hang on. Sorry. No. No, sorry. I had VLC, VLC, but it's not working too well tonight. So I'll have to skip that one. Anyway, so is anyone sort of really not getting the engine, or we can move on because we don't want to talk terribly much about the engine, but it's. So we've got the sparks and the ignition system that are one of the preferred ways of trying to get an input signal, so we can figure out what the rotational speed of the thing is. Sorry, let's go back. Whoops. Let's go through this. So we've got the car battery and the coil, which is really a transformer. So it's got a so-called primary winding and the secondary one, which is the high tension, which is the spark plug lead going off to the so-called distributor. This is a bit of a weird diagram. That the distributor are the two blue bits, and they're really collapsed together in one component. One of the things, this is the old-fashioned type of distributor, where there's a contact breaker, so-called points, which is just a switch, and so it switches the current on and off going through the coil primary, and then the coil secondary develops something in the vicinity of 20 to 30,000 volts, and it flows through a spark plug type lead or high tension lead to the top part or the rotor of the distributor. And this is sort of a switch, a commutating switch, where this rotary bit sparks across to a terminal when it goes past it, and that particular spark plug receives its spark. Is that making sense? Or that's so this distributor here, the blue bits, really looks like that. So there's the the rotor, as it's called, which is the part that's rotating around and going next to the contacts that allow the spark energy to go into the spark plug leads that are plugged into the 4 ones here. And the central one is the one that comes from the coil. And so even then, there's so that's sometimes the preferred way of picking up the signal for processing, for going into a tachometer. Sometimes they use an individual spark plug lead for sensing the signal. Sometimes they use the centre one from the coil. And there are pros and cons. If you use one of the ones to the spark plugs, you don't need a switch that selects how many cylinders there are in the car, in the tachometer. But the downside of that is that it's a hell of a lot more challenging to not have an interfering signal coming from one of the other sparks and a sort of miscounting. So that's a circuit diagram of typically how it looks. So this is the old-fashioned type of contact breaker, which is breaking the current in the primary circuit there. And it's just a mechanical switch with a little spring on it. The more modern systems, and when I was doing this, we were in the process of changeover. So some of our older engines had the contact breaker, and some of them had the so-called high-energy ignition, which was semiconductor switches replacing the contact breaker there. What's often in the industry called a condenser, we call it capacitor across there. And the primary, and the secondary, which is developing the 20 to 30,000 volts, which is selectively switched by the rotor to go through to the spark plugs. So, for people who are not familiar with that sort of stuff, does that make sense to you, or do we need a bit more explanation? Move on. Have to apologise that some of these stuff, this is all done in the days pre-IBM PCs. They hadn't been released. So a lot of these are hand-drawn stuff, and unfortunately some of the copies didn't come out terribly well. But anyway, this was one of the early models of a tachometer that we developed inside GMH. It was developed by my boss before I turned up. And you can see on the left-hand side is the input, and so the assumption is that it's going to be connected to the... Hang on, let's go back. In fact, let's talk about where we normally connect these things. Many tachometers are connected to this switching point on the primary. So you just have an alligator clip and you clip it on. One of the problems with that is that it's got some fairly nasty 400 volt spikes on it, and they are considered dangerous to personnel. So you wouldn't want to be hanging on to it if the engine was going, and so there's a safety issue in that, and also sometimes there's access issues as well. So other tachometer suppliers try and pick up the signals from the secondary side of things, the high voltage side of things, and one of the, in fact, just thought of it now. One of the techniques is that they have a pickup. There's an example, which is basically magnetic, and so it's a coil on some magnetic material, and you can see that you can open that up, and you poke the high tension lead through it, and you're effectively picking up the current in the spark plug lead. And it's just hit me that I'm not sure whether any manufacturers have ever had a go at trying to pick up the current in the primary side of things. Anyway, The ones that I'm familiar with clip around the high tension or the spark plug leads. So those are the two most common ways of doing it. The way we developed it, I wasn't keen on getting into the contact breaker because of the partly on the safety issue side of things, and we ended up developing a different way of doing it, capacitively picking up the voltage in here rather than the current. But anyway, this circuit was one of the first ones where it's connecting onto the primary side of things. This circuitry here is trying to pulse shape things to only have one pulse trigger per spark, and that's a fairly primitive circuit, and it might work most of the time, but it doesn't work. It doesn't work all the time, because I can tell you there's an awful lot of variability in the in the wave shapes. Switching for the different number of cylinders and range settings for the tachometer, and then we've got some circuitry here which is smoothing out the signal with a dirty big capacitor and resistor and going into a meter movement. So we had a meter movement. There's always an argument whether it's it's better to have an analog meter or a digital one. There are advantages of one and the other. Probably the best thing to do is have both. And then there's a fairly simple arrangement for the power supply. So we're taking the power from the car battery, so clipping it across the car battery. But within GMH, we had a lot of variability. So some of the equipment is installed in stationary booths and that sort of stuff, and so we've got mains power, and so sometimes it's battery powered and sometimes it's mains powered. So that's a block diagram, if you like, of a fairly typical tacho, and that's what we had. So you have some form of picking up the signal. So we're going from the signal coming in at the left and getting processed, and it does need to be thought about as being processed as coming through to the outside. So the pulse shaping or conditioning circuitry, which is basically trying to produce a logic output of one pulse per spark. And that's the challenging bit, to make sure it's one and one only and doesn't miss some, or it doesn't start to insert some extra ones, particularly if there's nasty interference. And then you put it into something that's a frequency to voltage converter, and you're then taking that out to either a meter or, in our case, quite often a DC output proportional to the speed of the shaft, which will be going out to a whole lot of other fancy instrumentation equipment. We had a chassis dynamometer, as it was called, which meant that it was a dynamometer, which is basically an electrical engine which becomes a load for the car, and the car's driving wheels, so front wheels, if it was a front wheel drive car, would be on this great big wheel, which would have been the best part of 2 metres in diameter, connected to this load, and that was the chassis dynamometer. The car was sitting there with the driving wheels on it with bloody big cables, because you've got to have the force of a car to keep it stationary, and the wheels locked, and they would do tests. They'd be doing 8, 10, 12 hours of testing a day for development purposes. In the ones that I was working with, a lot of it was to do with noise and vibration, and so they would be measuring vibration, acceleration, or perhaps the sound level with some quite fancy equipment running to thousands. Perhaps one piece of equipment was up to $1 million, and this is back in 1980. Analysing the signals, or the sound and the vibrations in the car over the speed range in different gears, and so you'd have a chart where it was the rev per minute on on the x-axis, and on the y-axis would be sound level or vibration and resonances and stuff like that. So that's why we wanted a DC output as well. So we didn't want to just have the meter there. So we had multiple variants of these things. So the different types of pickup, as I said, this is a commercial one. I avoided those because I figured that I wouldn't be sure what their characteristics were and whether I'd have a long-term supply of them and all that sort of stuff. So I started off not being terribly keen on those. And there's a different one. There's a third one. Now, the reason I've got this in is it's got a decent coaxial cable coming out of this. So there's a core, there's a ferrite in here, spring jaws, and so the spark plug lead goes through it, and there's a coil around the ferrite there. So it's a pickup coil for picking up the AC current in the spark plug lead, and this type of connector is known as a BNC one, which is very common in radio frequency gear, and is a really good sort of connector to have, which I'll come back to because it's worthwhile having things that have got decent RF radio frequency techniques. Otherwise, you end up getting interference and lousy signal results. So typical block diagram, you got some sort of pickup, and that signal there would be the primary signal, so that would be 0 to 12 volts, and a lot of ringing there related to the coil. And what we want to come out of the pulse shaper is a nice clean logic pulse waveform, which we're going to then try and figure out what's the frequency of that pulse waveform for the put it through a frequency to voltage converter, and then have a display. I spent months on this project. In fact, when I realised that it got spread over about 3 or 4 years, on and off. So as I said, the most challenging thing is to make sure that we don't get this sort of stuff happening. We don't get an extra pulse coming in. We don't get 2 pulses where there should be just one. Or we do get the pulse and we don't have any missing ones. And we did a lot of tests to measure that. Not quite sure where I've got that in there. Anyway, moving on to, so, hang on. Yeah, partway through the project, the reality is that you've got a lot of other people around the place who don't know much about electronics, and sort of say, look, why aren't you buying these things? You can buy them down at Kmart, you can buy them down at Repco. And it got a little bit wearying because we're sort of saying, well, none of them are working very well. And so in sheer frustration at one stage, I sort of stopped the project with the guy that I was doing it with, and we contacted a whole lot of suppliers and said, look, send us along your tachos, and we're going to check whether they're suitable for use in the test centre. There's a really old piece of equipment. I'll come back to that. So that one there is I'll come back to too, because it got the wooden spoon, and it was one of the most common ones around in the day, and many people would have seen it in garages and stuff. So that's the report, and it was surprising how bad they were. And as a class of instrument, I'd have to say they were sort of some of the worst that I've come across. A lot of them claimed an accuracy of about 2%. Well, all I can say is that's under really ideal conditions. And it was quite common for us to see 20% errors and more. Now, I'm not saying the whole time, because they weren't complete rubbish and a complete waste of time, but if you're depending upon the things, you can't be happy with something that's going to give you the right ballpark of accuracy only 90% of the time. And in fact, if you're plotting graphs and on the chassis dynamometer and taking noise and vibration and thing, and your equipment goes mad, well, there goes the last half hour's work, because you've got a graph that's just got scribble all over it because the equipment went mad. And so one of the important things that we had trouble getting the message through to other people was that the errors can't be calibrated out because they're erratic and spurious and not reproducible. The automotive environment is a really hostile environment for electronics, and so the electronics really has to be designed for that. And there's an awful lot of people who go through their courses and stuff don't get to realise just how things need to be done there. So we summarise it that there needs to be a decent pickup method of the signal. You need to have a decent circuit design, and you need to have a good way of getting rid of the interference, because you're dealing with sparks and interference. That if you've ever put a portable radio anywhere near a car with the bonnet up, you'll know what I mean. And sadly, it appears that most of the manufacturers of tachos don't seem to be able to get all three of those right. Some of the manufacturers do really well on two of them and not the other one, and so there's no consistency. There's no, they don't always stuff up the wrong one. They don't always stuff up the wrong thing, the same thing. Sorry. So we sort of did a choice magazine type exercise on commercial tachometers, and we specifically went after better ones because we knew we were trying to get something that worked all the time. So electromagnetic compatibility, which means that you want something that is not going to give you bad readings in the presence of sparks and motors going and that sort of stuff. The triggering is also taking that waveform, whatever it might be, the primary or the secondary, and shaping it so that you can get a circuit that only ever gives you one pulse per spark and always gives one pulse per spark and doesn't leave them out. So those two, the first two, are the what I'll say the things that were most consistently mucked up by the manufacturers. Accuracy, by that I meant the accuracy of once you've got this pulse train, does it give you a decent answer as to what its frequency is? And most of the manufacturers got that reasonably okay, although some of them didn't. And that's mostly about designers understanding temperature coefficients of components and how components change with temperature, and choosing components that have got low temperature coefficients and don't change their characteristics much with temperature, and also using decent circuits techniques. And in that space, most of them got it right. We also tested them for electrical robustness. We wanted to make sure that it could take 30 volts forever between any combinations of terminals. We also figured that it ought to be able to take continuous flashover from the high tension, from the spark plug. And the top one here, hang on. I'm getting annoyed by this. Sorry, I'm trying to pretend that thing doesn't exist. Yeah, sorry, I've got a little meter there that's okay, now I've got rid of it. The comment at the top there, a lot of people don't realise this, that when something goes wrong in the alternator area of your car, it can throw onto your battery lead line a 120 volt negative pulse for about a second. That's enough to wipe out a lot of electronics, right? So we wanted something that wasn't going to get stuffed up by that. Fortunately, this was done in the late 70s. Fortunately, car manufacturers have got to know that now, and in most cases, I think they've pretty well got it well protected. But that's always a problem. And so we. So that was the electric robustness. You also want something that is reasonably fast to respond. You don't want the needle to just creep up when there's a change in speed, because the engine engineers and stuff want to know if what the speed fluctuations are. So they don't want something that's very, very slow response. And it just so happens that that's one of the tricks that is pulled by the less than capable tacho manufacturers, that they can hide the fact that it's not triggering terribly consistently by just getting it to average over a large number of seconds. Safety to personnel, and decent instructions and labelling. So we went through all these tachometers, about 16 of them I think we went through. Since GMH was being supplied with Bosch equipment, we didn't have much trouble talking the Bosch people into lending us some tachos, so they lent us a whole lot of tachos for test. Sun and Bain were a couple of other well-known brands around at the time. We put in our own board for test as well, and gave it the same look through, and came up with some criticisms that we needed to improve. We also put in a tacho from the dashboard of a current Holden, from the instrument panel, and I tell you what, it was absolute crap. And we also managed to find a tacho from the General Motors Proving Ground in Milford, which is somewhere over in the States. So we weren't the only ones trying to develop our own tachos. So we got hold of theirs to see how it performed, and we went through the whole lot of them, and there was only one that got anywhere close, and even then we couldn't give it a recommendation. It was one of the Bosch ones, but all of the others failed significantly, except our own, of course. And although people would claim we were biased, in fact it was the opposite way around, because it was one of those things, the more you test something, Shivers has got that wrong with it, would toss it in the bin, right? So as soon as you came across something that was bad, you sort of say, look, cease the test, it's not recommended, because it's just too bad with that. Whereas we knew ours pretty well, so we knew what its deficiencies were, and we wrote them up. But here's a few examples. Would be a good tacho, except that placing the pickup near the ignition leads causes errors. Well, although it's a car, right? So electromagnetic compatibility is very poor. The triggering was pretty good. And it used quality components. People who are familiar with capacitors of the day, the polycarbonate capacitors were one of the preferred capacitors as a low temperature coefficient. Yeah, and so with most things with electronics, when you're doing precision measurement, you try and design your things so that there are probably only about 3 components that dominate the accuracy of the thing. And quite often, and certainly in this case, it will be a precision resistor associated with some sort of timing measurement, a capacitor that's also associated with a timing measurement, and an integrated circuit of some sort. And usually what you have to do is you have to choose those ones well as being low temperature coefficient, and the rest of the circuitry should not need to be low temperature, high precision components. And so the polycarbonate ones, yes, they're more expensive, but you just select them for the places where they're needed. And so, yeah, we pulled the things apart to have a look at what sort of components that they were using. Inaccurate or complete malfunction when close to suppressed ignition leads. Well, no, can't have it. Labelling is poor. Hang on. Yeah, and the labelling was poor, and it was an unconventional way of connecting the thing. So look, that's, you know, people are going to make mistakes with that machine. Not recommended. Poor accuracy and so on. And now comes our sun tester. Accuracy extremely poor. Recommended that any such unit should be destroyed. That really was the pits. If we went through the electronics design, it used low quality components all the way through, and so we put down 7% errors against the temperature changes. Dwell angle, which is an angle measurement related to the distributor, introduces another 2.5% of error, and battery voltage, another 2% of error, quite apart from the fact that it had poor triggering. So,
Colour was good, wasn't it?
oh yeah, the colour was good. Yeah. And now the Holden dashboard one, and it was really irritating at times. You'd come in with a test engineer, and they're very competent mechanical engineers. But they'd sort of say, "Look, your tacho's giving the wrong answer. The dashboard tacho says this," and you're sort of saying, "Hello." Does anyone know the word stiction?
Yeah. Sticky friction.
Sticky friction. Yeah. And very poor quality meter movements have stiction. Decent meter movements have dual bearings, and they're very, very, very low friction. But if you've got a bearing in a cheap analog meter, and that you've got a sticky bearing in it, that's what they refer to as stiction. And so have a look at this. As we increase the rotational speed of this meter, so that it's going from 200, 400, 600 up to 4,000, it's actually measuring 250. Geez, have I got this back to... oh, yeah, yeah. Yeah, see it's lagging here. So it's 50 too low, it's 50 too low, 50 too low, 300 underneath it. So 4,000 revs is actually indicating 3,000. But when we come down in speed, it's reading high because it's sticky, right? So look at that, 4,200 coming down, whereas on the way up, it's 300 below. Yeah, right. So
Similar issue with aircraft altimeters.
yeah,
That's sticky, and then you don't know what you are.
yeah. So absolute crap. And hang on. Oh, this is another thing I haven't mentioned too. With the old-fashioned points or contact distributors, when you've got the engine going fast, you got this. It bounces. Yeah. It bounces. So you get 5,000 or 6,000 revs in some cars, and the distributor contacts are bouncing. What do you think that does to your waveforms? Right? And so that was one of the things we were testing for. And we had a test machine. It was realistic except for the distributor, except you can't fully test it properly because your spark plug is not in a compressed environment. You've got the spark in free air. So it's a very different voltage. So the sparking is different. But anyway, on that, we're able to use the distributor machine testing them for points bounce. And some of the commercial tachometers did pretty well on it, and others didn't. So this particular one, poor triggering with points bounce, whereas other ones, it came out pretty well. So different manufacturers get different things right. In fact, it wasn't even by manufacturer. It was different models were good for, and in some ways and poor in others. Similarly, our testing of the Milford tachometer from the General Motors division, it excelled, and it was much better than the others in electromagnetic compatibility. See there, we rated it as excellent. And the triggering was fairly good, whereas most of them, many of them failed on the triggering. But it failed on some other areas. So we went through the lot, wrote our report, hopefully convincing people that we really had to keep this project going. So let's move on.
Just before you do, John.
Yeah.
Quick question. What was your reference to know what the correct speed should have been that you were trying to measure?
Oh. It was more a case, Graham. Many cases a tachometer would, for a fair bit of the time, give a plausible reading, and then it start flickering and carrying on, right? And so that was our measure of triggering, was just observing whether it suddenly went erratic under some conditions. But and so our accuracy, we weren't actually directly measuring accuracy directly. What we were doing is we were evaluating the accuracy of the techniques of measurement. So we would sort of say, look, if they're using scruffy resistors and timing components and stuff like that. But we had our own gear as well that we were comparing from them. I mean, by this stage we were getting confidence in our own measurements. If we're talking about directly measurement of engine speed, yeah. But a lot of the evaluation was actually not necessary with an engine. It was, we had a distributor testing machine, and that's where we'd test whether it played up with points bounce and that sort of stuff. Yeah. But for calibration purposes, our own gear, we had a calibration input where we could put in our own fake logic signal, which was clean, and so we could calibrate up the trailing circuitry, the frequency to voltage converter. See, that's the thing that a lot of people don't understand, is that you've got to have very reliable triggering, 1 pulse per spark, and then the accuracy is entirely determined by the accuracy of your frequency to voltage converter. If you deviate from a reliable 1 pulse per spark, then all bets are off. And no matter how accurate your frequency to voltage converter is, it's rubbish, because it's reading the frequency of the wrong thing. Power supply was fairly ordinary, straightforward. Unfortunately, a whole lot of my circuitry I drew up on graph paper. This is before CAD/CAM and stuff, and so that's not as... Oh, what have we moved on to? Yeah, where am I on to? I was going to make some remarks about electromagnetic compatibility. One of the best ways of keeping things quiet is to get a die-cast box. It's the best $25 you'll ever spend. Die-cast aluminium, fairly good tight lid, bolts around it. Yes, you drill some holes in it to get wires in and out. These keep things electrically quiet like nothing else does. Nothing else. That plus... what happened to my... I thought I had a picture of some coax, but is everybody familiar with coaxial cable? I'm sure I've got a picture in there somewhere of it. Did I?
This is the NC connector.
Oh, okay, yes, I had some that was stripped. But anyway, coaxial cable is It's typically about 4 or 5 millimetres in diameter. There's different diameters, but you know, the common stuff is 4 or 5 millimetres outer jacket diameter. And so you have an outer jacket, typically black plastic of some sort, and then you have often some woven copper as an outside shield, and then some dielectric, which is plastic of maybe a millimetre or two diameter, and then in the middle is the conductor that you're interested in, which is copper as well. And it's not that expensive, and there are all sorts of different grades of it. We use one of the most common grades, RG58, and those two things are probably the two things out of the electromagnetic compatibility side of things where we beat the hell out of almost every manufacturer because they didn't do that. Believe it or not, the sun tester got close because at least it was a metal case, but a lot of them are plastic cases. Now, plastic cases are just not in the game if you're near sparks. You know, similarly with coaxial cable, and there was a remark before, we developed a probe that has an alligator clip that actually clips around the spark plug lead, then connected to coax, and we only connected the shield back at the case, the tachometer case or the instrument case, and that in most cases worked pretty damned well and beat the hell out of most of the other pickups that we found from commercial equipment. There were one or two cases where we did get into trouble with that, with picking up the high tension from the spark plug, because in our case we were not only trying to get a measure of rotational speed, we're trying to measure a whole lot of other things. You know, we've got several tens of thousands of dollars of other equipment around the car trying to measure it, and we're trying to measure the whole lot of everything together. And the fact that we were conducting by this cable connected to the spark plug lead, it upset some of the other equipment. So that one did get us into a bit of strife, and I think I'll be able to show you a bit about that in a moment. But in that particular case, we found that connecting the shield at the hot end, you know, where we're picking up the signal as well as at the instrument end, made a huge difference. And when I say huge, 100 to 1. Yeah, so something's gone wrong with my. Look, power supplies. Something's gone wrong here. That's a power supply that we used. Occasionally you are really restricted in your design that you really want a negative voltage, and this is one of our more upmarket power supplies that we developed. And so we've got the car 12 volt system coming in here. Quite a deal of protection. That fuse and the fairly fat Zener diodes, they were 33 volts, were they? Yeah, 33 volt Zeners. We decided we had to test that, and perhaps the way to test that would be, well, I guess the most brutal test you can think of is to switch the mains to it. So we did. And it survived. The equipment downstream survived, the fuse blew, and that's all it needed. And so the Zeners, yeah, we tried 10 goes of mains, and the Zeners survived. There are times where you don't know whether your techniques are good enough, but that sounded like it was okay. And then typical 3-terminal regulators, but most people would know that you can get DC to DC converters that will give you a negative voltage, even if you put a positive voltage in. And so the Intercell is one of several. They call them well, there's several types, but the charge pump is one of the ones that's around. So occasionally you get into a situation designing circuitry and you think, oh my gosh, this is so hard because I can't get a negative voltage. So that's one of the things you can actually generate one. So we got about a minus 5 volts out of this. So we had a plus 5 volts and giving it a minus 5 volts. And they're not expensive. They're only a buck or two. This is the type of alligator clip we were using. It was a 25 amp, ordinary cheap alligator clip, and from Utilux, and it has a boot. We figured that's probably a better thing from the viewpoint of personnel. I won't say it's completely safe either, but and so we filed off the teeth and clipped it around the high tension lead. And after coffee, when we take it, my order of slides here seems to be completely stuffed up, so I might sort it out after coffee. But anyway, yeah, we might have a break soon if you like for coffee. What was I going to say? Yes, and the idea was, and it was somewhat unconventional. I'm not sure that I've seen it anywhere else. Roughly speaking, we decided that you used to the idea of if you've got a big voltage and you want to measure a small voltage or a fraction of it, you have a resistive divider, right? Well, what about a capacitive divider? So you have two capacitors, a big capacitor at the bottom and a little capacitor at the top, and so you've got a 1,000 to 1 voltage divider, AC. And so that's what we did. So we measured that alligator clip is capacitance to the centre core of a spark plug lead was about 3.4 picofarads. You can measure those things because you can buy spark plug to alligator clip meters. No.
GMS could afford a $500,000 RC bridge.
No, you think up techniques, and it's a lot of yeah, exactly. An RC oscillator, and you measure it, and it's all in my report. Yeah.
So was there a difference between using the older wire ignition leads and the newer carbon leads?
I don't think so, because it's mostly geometry, and a lot of those things with the geometry, they're not incredibly sensitive to the geometric dimensions.
Is that repeatable?
Yeah, reasonably so. Yeah. And yeah, so that's what we used.
But you didn't need a calibrated voltage anyway, did you?
No.
You just needed a reasonable
Yeah.
value.
Yeah. Somewhere in my slides, I'll show you that a very small sampling of hundreds and hundreds of waveforms that we took. We went through and tried to figure out all the different combinations of things. So we're looking at primary and secondary voltages. There's points bounce, as I said. The spark plug gap. You set your spark plug gap to be a certain gap by the manufacturer. Now, for sure, that's going to vary. So we varied the gap, and that changes the voltage quite a lot. The engine load, you get quite different waveforms in the ignition system if you've got wide open throttle, full bore, compared with an idle type of thing. And even worse, if you've got a flywheel effect, and it's what they call pinging, where you've got an engine that's been going flat or flat chat. And so what was the thing? It was an awful test. Hang on, what was it? Close, yeah. full revs, 6,000 revs at zero throttle. goes the engine, right? And pinging like fury. You know, all of those things change your waveforms quite a lot. There was one waveform that I never did find the explanation of that happened just occasionally, where when you've got the breakdown. This is the secondary voltage with time. How's it go? It goes screaming down to something like about minus 20 or 30 kilovolts, and then the spark plug breaks down, and you get a voltage, and I can't remember what it was. It was probably several hundred volts. And we can't measure these things terribly well, and these are the days where storage oscilloscopes were pretty damned expensive, and a lot of our stuff was actually done with storage oscilloscopes and the old, what was the camera, the instant camera? Sorry? No, the Polaroid, thank you, yes, the Polaroid cameras, yes, we went through buckets of those. And hang on, what happens then? At some point you get quite some ringing when the spark gives out. But one of the things that I found was that occasionally you got much bigger amount of. It was an anomalous situation. It wasn't all that often, but it was 2 or 3 times as much voltage here. Then when you get points bounce, you know, instead of having just one decaying thing there, you get another one. And you get another transient. You know, one of the transients is when the spark gives up and runs out of energy, and then you get another transient when the contacts close. So and so depending on your speed, you get different numbers of pulses. But that was an illustration of, you know, just doing lots and lots of tests to see all the weird waveforms we could generate. Anyway, I was going to make a couple of remarks about power supplies, and I'm not. That was that one. I don't know about the other one. Well, look, there was another one. I'll see if I can find it on YouTube, because we tried to get it in VLC. Bill Donlan might be interested in this. Now, where the hell is it? Now, I don't know whether we've got sound or not. Have we got sound? I think.
Amazing how much of our world is powered by something so small. There are a million uses for these little wonders. Well, make that 1,000,001. Introducing the Mercedes AA class, the first fully electric luxury sedan powered entirely by AA batteries. No more plugs. No more charging stations, just 9,648 AA batteries. Zero emissions, lifetime drivetrain warranty, and a top speed of 52 miles per hour. Everything you've come to expect from Mercedes. Onboard satellite navigation, Bose stereo system, and ample trunk space to store extra batteries. Luxury sedan to receive the prestigious AA Plus grade from Batteries Magazine. The Mercedes AA also ranks best in class in safety, thanks to standard curtain airbags. The touchscreen in the center console keeps you constantly informed of each battery's power level. You'll know a battery's dying before it's dead.
In 3 miles, replace batteries 900.
You can replace them individually or all at once with the ribbon release auto dump feature. batteries not included.
Yeah, okay. So let's go back to getting into the actual circuit that we developed. As I said, basically it's a pickup and a pulse shaper, and the pulse shaper is the one that's perhaps the most challenging. Then a frequency converter. Quite often the frequency converter is some sort of triggered monostable, something like that, and a filter that just you'd be familiar with it with pulse width modulation and the like, where you've got a pulse train and you filter it to get it to the point where there's the ripples almost disappeared, and so it becomes a DC. Yeah, so as I said, we used an alligator clip, a 25 amp alligator clip from Utilux, and they're still available from Radio Parts, same part number, and some 2 or 3 metres of, or up to 5 metres I think it was, of coax. Actually up to 8 metres I think I specified, yeah. And there was a story behind that. And we, hang on, yeah. So, roughly speaking, our capacity divider is the 3 picofarads there and the 10 nanofarads here to ground. And so we're getting fractions of a volt AC here and up to 20 kilovolts over here. Now we do need to correct it a bit because there's capacitance for the coaxial cable. There's also capacitance for these from these protection diodes, Zener diodes. Measured and specified all of those, and they are a relatively small effect. I think I allowed up to 800 picofarads for the coax. It's about 100 picofarads a metre. So I allowed up to 8 metres of that, and I did look it up in just the last few days. It was a few hundred picofarads, I think it was, for these protection diodes, because I think they were reasonably high power ones. I can't remember. No, they may not have been that high. So let's go through them in order. I'm going to come back to the issue of the capacitance here with the around the spark plug lead, because there's a question of what do you do with the shield here. It'd be kind of nice if we didn't have to connect the shield. We're certainly connecting it to the box, to the ground of the box. This wasn't the box we used for our tachometer. We used this circuit, of which this is actually this. Yeah, the conditioner pulse shaper circuit has got 3 slides devoted to it. So that's the input, that's the middle, and then that's the output. So the input is the voltage divider, and it's followed by some filtering. And I've designed the filtering. It's a so-called 5-pole Bessel filter. And so that looks like 2 of the poles, I think. And then there's some more filtering. So the other poles. Is that? I'm having trouble picking where the 5. I can see 4 poles there. Anyway, and then we're going into a Schmidt trigger, some hysteresis to sharpen up the signals, and also give some a tolerance band, if you like, in terms of size of spikes. And then I've got a line driver. We quite often used TTL outputs and drive them into coax and send pulse signals at a distance. So that was a matched, a 50 ohm matched drive for TTL. So that's our pulse board and the pulse shaper board. We probably made 30 or 40 of these, so they weren't really quantity, and so it was more, if anyone went through this and sort of said, "Hey, we want to minimise some costs," we didn't spare the number of components. But if you're doing serious production of this, you probably go through the whole lot again and sort of try and economise a bit. But yeah. Anyway, to go through some of the unusual things, as I said, the one unusual thing was the capacitive divider, and I've drawn it up there. So the top leg capacitor there is 3.5 picofarads, and as I said, we did measure that by a couple of different techniques, and both of them came out with pretty close to the same answer. One of them's doing square wave type tests, and another one's doing sine wave type tests, with, as Joe said, with known resistors and frequencies and stuff. Coming here after the coax, we've got a fuse, and that's for that's protection. In actual fact, it's a high voltage resistor. I looked at the notes and think, oh, geez, did I do that? One of the problems with putting a resistor in there is that the resistor has a voltage rating, and hello, we've got kilovolts over here, right? So I figured, well, if I put in a fuse, it can flash over from one terminal to the other, and that's okay. And so I measured it. So that 50 milliamp fuse is otherwise known as a 120 ohm resistor. And I don't think we've ever blown one up. It's there as a resistor so that, it's some protection, and now we have got a genuine resistor here, which is providing some a bypass, and we're getting a bypass down to earth fairly quickly from that polyester capacitor. So we're trying to keep RF out of the box if we can. And you'll see in a number of spots where I just put in an extra bypass capacitor because I just don't want spikes there just in case. And so if the accountants came through later, they might have an argument of trying to save a capacitor, but I don't care, I'm just putting it in. So for example, that's, that's a reasonable size, but yeah, that one there, that one looks like it's to get rid of high frequency. Yeah. Another unusual thing is quite often when you get into design of this, because this is linear design, and we're using 5-volt rails here, and 5-volt rails with the LM324, it's still a current chip, very popular and for good reason. It's can be a bit restrictive dealing with things. So you've got a narrow range of voltages to deal with, somewhere between 0 and 3 to 0 and 5 volts. And how do you deal with AC when it's single-sided? Well, see, this point here is roughly called, I think they can often refer to it as a false ground. In fact, it's 2.3 volts, because further down the track I've taken the 5-volt rail. What's going on? I've taken the 5-volt rail and voltage divider, and so this quarter of the LM324, this op amp, is just providing a regulated, if you like, fraction of the 5-volt rail, and it's 2.3 volts. So Whereas lots of things would actually be going down to a ground. In fact, they're going down to this 2.3 volts as a way of shifting the voltage up and sort of creating a situation where I can have some AC coming in and not have it clipping. So it means that I'm keeping the op amps operating with outputs somewhere between approximately 0 volts and about 3 or 4 volts. So the maximum output you can get from the LM324 is about 4 volts from memory.
So do you not need a bypass capacitor on that 2.3 volt rail? It doesn't appear to be running that.
You mean this one?
Okay.
Yeah.
Okay.
But you do make a good point that there are times where it probably is smart to put a capacitor on it. Now, putting a capacitor straight across there to ground, that could have some issues, because when you capacitively load an op amp, it quite often makes them unstable. So an extra fiddle for that is, if you were doing that, Graham, you'd actually put a capacitor to ground there, and you'd put a smallish resistor, perhaps a few hundred ohms, in series with the output lead. So it would still regulate, but it would have it so that the op amp is not loaded directly by a capacitor. Yeah. And I can't remember, but this is probably deliberately a bit of a pull-up resistor, to get a bit of to get a bit more output out of the thing. Oh, hang on, yeah, okay. This in fact is a this is a Schmidt trigger. This is the hysteresis. See this feedback resistor here going to the plus terminal, not to the minus terminal. So that's you're familiar with that? That maybe not. Maybe. If you've got a sine wave like that, for example, or any sort of shape like that, you might decide that you would like to have your output go high when it gets up to that point, but once it's got, sorry, let's dot that. You would like to have it that it has to get up to that level before you get a logic high output. This is called what's known as a Schmidt trigger, or and it produces what's known as hysteresis. However, you might like it to have to go down to, for example, this one before it starts heading down. Does that make sense? If you had it that it just did that and that like that, then what would happen if you had a little bit of extra superimposed noise? Perhaps this isn't a perfect sine wave, perhaps it's got some wiggles. And so if you've got wiggles like that, you've got a real risk of having a really short pulse like that. Does that make sense? So one of the standard techniques of handling that sort of thing is saying that once you've got something that's gone high, it's got to go a long way low before you allow it to say, oh, it's gone down low. And so that's what's known as the hysteresis width. And so, you know, the way I've drawn it there, it could be half of the half of that size of that peak there, and that gives you a high degree of immunity to extra nasties getting on there. And those nasties could be coming from interference in terms of amplitude. And the other nasties, and so that's those two techniques are that technique combined with filtering. So if you put a bit of an RC filter at the front, that tends to smooth out the fast spikes and reduce them. So if you've got some ginormous ones, then if you put in this RC filter, if that's there, then by the time it gets to there, these are going to be reduced quite a deal. If they're fast and high speed ones, and then if you've got this hysteresis width, so that it means then that you can have a sort of a noisy waveform there and still have just one pulse coming out of it, not a whole lot of little fast ones. So that's one of the things that I've used through there a few times, and so that's one of the things that the hysteresis achieves, is it helps you with certain wave shapes to choose that where you've got a risk of multiple pulses and you sure as hell don't want that, you can get rid of those. So I've deliberately designed, I think it was something like about half a volt of hysteresis from this circuit here. So that's one of the ways of eliminating nasties.
If I might just interject there, that's actually making use of the effect that you were really upset about in the cheap crap GMH meter movement, which had his stiction.
Yes.
It's actually electronic stiction, but used to good effect.
Yes.
And in the meter movement, it produces hysteresis, exactly what happens.
Which is what you don't want then. Yeah.
Only not very well controlled, I might say.
In fact, being philosophical about that, David, I thought about it that almost everything that I can think of that I've come across in electronics, you get some effect and you're thinking, in some cases that's awful, but boy, I could use that somewhere else.
Marketing idiom, if you have a defect, you promote it.
That's bullshit.
It works.
Yes. Yeah. Okay, so that's a fairly standard technique. Oh, and see here. Here I've got some filtering on the input to this hysteresis. So even though we've got a long way through this chain, I'm still putting in protection, trying to get rid of nasty pulses which probably aren't even there.
Good conservative over-design.
Oh yeah, and look, that was one of the messages, David. Is you over-design things and then you've got it working properly, and then if you have to, you go back and refine it and sort of say, look, some things are not required, but in a development environment, so we were serving in a development environment, it's probably not going to go into volume. But so to just take that line, around about that time, Bosch produced some experimental prototype electronic fuel injection and spark advance modules for GMH, because we were in the transition period of moving from mechanical distributors over to electronic spark advance. And whoever designed it obviously wasn't a terribly experienced designer and in the electronics side of things, and from what I heard, Bosch Australia decided that the German one was too expensive and they'd have a go at building their own, and it was awful. And I actually got called in to try and debug it, and they didn't have shielded boxes. They had unshielded boxes with power supply leads coming in with decoupling capacitors. The guy had obviously learned about decoupling capacitors, so he had his power supply coming in, the raw plus 12 volts into this thing, and he had a capacitor. I think the leads on it were about that long in terms of the board. What sort of a capacitor did you have? 1,000 microfarad electrolytic. So for anyone who knows anything about those, they're the worst capacitor in existence for RF. They're great for audio. I knew some people at Telstra Research at that time, and I sort of said, look, you need someone to get this fixed. And I said, do you know anyone? I said, Telstra Research. And the guy at Telstra Research listened to it for a while, and he sort of said, look, you ought to speak to John Hollow. He knows something about that too. And due to the politics of the stuff, the place, they just preferred to go to Telstra Research and pay money. The guy that I pointed them to probably knew more about it than I did, but I probably knew enough. But the politics, oh yeah, we found a specialist and we're using them, yeah. But so that's a little bit of an aside. And the output stage, you can parallel up CMOS logic gates. But I put extra resistors in there. I wanted the thing short circuit proof and also to match the load. And so that's effectively a 50 ohm TTL driver. And so that's getting fairly routine. So the front stage of it is sort of pretty unconventional, slowly becoming more and more conventional as we go. What else was there about that? We've done the fuses. Now, does the ground there need to be connected? And the answer is sort of yes and sort of no. That's an excellent question. And in fact, I might even have the answer to that one, Graham. I thought to myself, it'd be kind of nice if it doesn't need to be connected, and does it really? And then I thought hard about it, and I thought, hang on, every point in every body has got capacitance to something else. Quite often it's quite small, but it's got capacitance, right? And then I'm thinking, well, what happens with a... I thought I drew a car over there. Oh yes, sorry. Yeah. By and large, if you put electronics in the car, you treat the car body as the ground, and you connect things to the car body. But we've got a tachometer which might be a metre away, it might be 8 metres away, and it might be part of another measurement system which is connected into ground, as part of our test facilities. And then I thought, it's time to go back to the old physics books. A sphere has capacitance to the universe. So you go to the old textbooks and you say, okay, there's a sphere and there's the flat ground. What's the capacitance? And you can find formulas for them. People who good on their different integral calculus and stuff figured out formulas for them. And thought, well, I'll plug in some numbers, but I couldn't find a paper that analysed the integral calculus of the shape of a car. So I figured I might as well take 2 metres sphere as a rough approximation to a car. So I figured, well, if I've got a metal sphere of 2 metres and its capacitance to the ground, and I'm going from memory here, 'cause memory from only a few days ago when I was reading my own notes, I think it was something like about 24 picofarads. I thought, okay, that's so much more than my 3.5 picofarads to the lead that if I consider this car's body as having a capacitance to my ground back at the instrument of 24 picofarads. Then I've got 3 picofarads in series with the active arm and 24 picofarads in series with the ground return connection. Hey, that's a hell of a lot bigger than that. So, to a rough approximation, that could be considered infinite. And so I went through a few numbers like that, and I said, well, okay, let's do another one. I've got this tachometer, and so they were an aluminium box that was about, well, it's basically a big lunchbox size. And so I said, look, let's model that by a 20 centimetre a 20 centimetre sphere, and hang on, can I find it? I think that was the one that came out at 9.3 picofarads. So this box to an infinite ground away was 9.3 picofarads. I figured, well, once again, that's a fair bit bigger, but not hugely bigger than the 3 picofarads. But if you consider that as a capacitive divider, then that's roughly speaking a third of this one. So maybe we lose 70 or 8. Maybe we lose 20 to 30% of our signal level by not connecting this lead. And sure enough, it worked. So what I'm getting at is that, yeah, the mechanic when he hooks up the when he or she hooks up the tacho, they may or may not connect the thing to the car battery, in which case it's trivial because the car battery's the negative terminal is going to come back to here. But if they don't connect it because it's gone off to some other piece of instrumentation, everything is still working. It's just the signals are 20 to 30% smaller amplitude. And yeah, and provided I've got a large margin, which I did, I probably had a 4 to 1 margin. It made bugger all difference. There was, as I said earlier, an issue that sometimes there was some fairly fancy measurement equipment over here, and the fact that we had a cable that was, sure enough, it was connected to the ground to this box here, but it's connected to this up to 20 kilovolts signal here, conducting into here. There's another box which didn't have its nice die-cast boxes, because these other instruments, they might have had good brand names on them, but they didn't necessarily have decent RF techniques because they weren't actually being designed for being used near cars. Brill and Kerr, you're familiar with their for sound equipment? Yeah. So we had some Brill and Kerr sound level meters and Brill and Kerr charge amplifiers for accelerometers and stuff, and they were. There were times where the ignition signals were getting into them, probably via this path, and that's the case where we broke it and put in a BNC connector and another one of our famous alligator clips, and actually soldered it to the BNC through connector. And then to Graham's question, was it Graham? Oh yeah. Where do you connect that onto on the car? But yes, we connected it onto a point on the car, and it made a huge difference of quietening down the signal that was leaking into this equipment, because some of them were sufficiently serious it was just writing off their measurements. Yeah, but for most purposes, we didn't bother with connecting the extra lead. In fact, somewhere, I can't remember whether I've got a slide of this or not, but somewhere I had a some measurements that we took for different equipment. I think it is in there. And if we took our reference amount as how much interference was getting to something as 0 decibel, connecting that that alligator clip with the BNC with the shield, a meter or something or other from their probe where we're around the spark plug. 24 decibel reduction, just clipping it onto the radiator cap. 24 decibels for the master cylinder brake line. 30 decibel onto the engine block. Negative terminal, the battery was 24 decibels. The best place was the nut on the top of the McPherson strut. 40 decibels, or for people who are not into decibels, a factor of 100 to 1. So that was a hell of an improvement for that. So that's the answer is, Graham, is McPherson strut, at least for that one.
So the significance there, I presume, is that was close to a large, massive development.
I think so, yeah. Yeah, I think so. The other thing that was of interest with respect to that was if we had a length of wire and then our alligator clip and connected onto our magic McPherson strut or whatever, the length of that wire made quite a difference. And so just no. So with 0 length, as I said, was 40 decibels improvement. With a 15 centimetre wire, that 40 decibel dropped down to 34. So there's a 6 dB degradation due to 150 millimetres there. Going through to a 90 centimetre wire, 12 decibels. So we've gone from 40 down to 12.
It's picking up.
Sorry. So
Picking up directly then.
I would say it's basically the inductance of that wire. Is that as you reduce that, it's providing a very low impedance path to the body shell, and if you increase this, and we're talking about, I think it was 1.2 millimetre wire, so it wasn't 1.2 millimetre diameter wire, so it wasn't it wasn't thin stuff.
Could be RF pickup.
Look, it could be any of those. We didn't really go into it, but yeah. But it illustrates understanding the equivalent circuit of these sort of things, that all of these things, you've got resistance, inductance and capacitance. Do some calculations on it and you usually leap out as which one's the most likely. And my guess is that this is most likely the inductance. And that 40 decibels, that all went away if you if you looped your wire back over the engine and or the spark plugs, it came back bad again. Yeah. So yes, there was certainly some experience with that. So let's move on. As I said, there was a filter and the Schmidt trigger, and I'm going to show you, just very quickly glance over a few pages, and unfortunately these have barely come out in the process of photocopying many years ago, but you can see there's a trace there, and I've done capturing the different conditions and the wide range of change of speed and the test conditions. Sometimes it's wide open throttle, sometimes it's not, that sort of thing. And a whole lot of different waveforms. There's only 3 pages that I've put up there, and you can see there that occasionally I'll put in the code, is it operating correctly? No. That was pretty unusual, but we went back and thought that that was a fairly extreme condition. But most of them came out that they was operating correctly, and that was used as part of our design process and how we chose the filter. And so when we had these sort of waveforms, I had a decade switched filter, that wide range filter that gave 4 or 5, I think it was 4 pole low pass filter of any number you chose, from half a hertz up to several tens of kilohertz or something like that. And so I could fiddle around with different filter bandwidths, and that's what I used that to tune it up to sort of make sure that the extra wiggles and stuff were well controlled by this filter, and then I was able to choose the hysteresis as well to avoid that. And so it meant that there was a very wide range of test conditions which produced weird, horrible pulses that we were still able to get rid of. Moving on to the end part of it, the frequency to voltage converter and the filter, this is fairly routine sort of stuff. You trigger a monostable, you try and make it an accurate monostable. You use CMOS so that it's accurately between a naught and the positive rail. You make sure that you know what the positive rail is, or it's a temperature control one, a good stable one with temperature. And so that gives you a quite precise way of turning frequency into voltage. You have that followed by a well-known gain low-pass filter, which just filters out the ripples, and you're just left with a DC. And that's what the later stages of that circuit. Why is my thing dimming all the time? So this is part of the filter, and then the Schmidt trigger, and so that gave us a lot of confidence. I mean, there were weeks and weeks of work going through all sorts of combinations. When anyone reported some weird thing and playing up, I'd go down and look at it and try and put a scope on it and stuff. And so we were able to find out what was going on. So now we get to, how do we design it to be accurate? And that's fairly routine. You choose yourself a decent chip. I used an LM322. Sadly, it's now obsolete and you can't buy them. So I think I would go across now to another monostable that made a claim to fame. So, for example, there's the CMOS 4538. And there's a spec. So that's the sort of thing that would excite me, that where the manufacturer is making a claim that the typical pulse width variation over the temperature range is plus or minus 0.2%. That's not too bad. Generally speaking, I was aiming at an overall accuracy of about 1 or 2%. And so the chip, if it's a decent one, so I think that's probably about 3 or 4 times better than say a 555 timer. Anyway, it was, you look around for something that provides a good, reproducible and temperature stable pulse time. You can certainly calibrate the thing, provided you're confident that it's going to hold it with temperature. And similar comment about components, the resistors and capacitors. Now, resistors have certainly improved over the years, and so In those days, 1 and 2% resistors were a bit exciting, whereas now they're routine. I'm not
Except if you're buying your 1% resistors off eBay. Let me tell you, I bought a pile of them and I just no absolute measurement, just sort of all the 10Ks and measure them, and they vary sort of by about plus and minus 1.5% from nominal. So the 1% is an illusion if you're buying them off eBay.
Okay.
Yeah.
Something weird's happened with capacitors, and I'm not sure whether improved or whether we're as good as what we were in those days. Polycarbonates have disappeared. From what I've read about it, polycarbonate, which was certainly my preferred one of an accurate temperature stable resistor in the nanofarad up to several microfarads type range, it appears that there was only one manufacturer in the world and they decided it wasn't worthwhile and they gave a shut-up shop. I don't think it was. I'm not sure. I can't remember. But there was only one manufacturer in the world and they gave up. And so they don't exist anymore. I am hearing claims that maybe it's a specialist or a particular type of polyester. But anyway, there are some polyesters that claim to get somewhere near what the polycarbonates did. But anyway. For the monostable, you choose something that's approaching precision components, temperature stable. It's hang on. Yes, so just a little bit of reflection on how things have changed, how I would do it differently. I'm surprised at how many things that were common chips those days are still common chips. The LM322, I think, is one of the very few that I've come across that I used in those days that are now no longer procurable. There have certainly been some improvements and things that have happened. So in those days, a microprocessor system, let alone a microcontroller, a microprocessor system was something that was big and a board and took a lot of work and all that sort of stuff, and would never have fitted in any one of these sort of boxes on their own anyway. Now you can get one chip that can do 10 times as much, and it's got analog and digital and the whole lot. That sort of thing would have increased the design flexibility quite a lot. I can imagine that trying to match up those waveforms with circuitry to give the reliable pulse, 1 pulse per spark, which was the most difficult thing to achieve. I can imagine that there's some smarter things that I could have done that had with a digital chip there, possibly giving some sort of adaptive gain or adaptive filters. See, I had fixed filters, and you could have adaptive filters, and even changing the hysteresis levels for that sort of thing.
We could measure the time and ignore any overrides.
Funny you should say that, because that was my next line here of points. One of the things that I would like to have considered would be, and I haven't seen many people write about it, is when you're measuring lowish frequencies, it's probably worth considering trying to measure the period. So counting a high-speed counter with a crystal oscillator and sort of say, look, it's 1,002 of those things, and so you then put that into a digital chip and say, give me its reciprocal, and that's frequency if we need that, and the other thing that can go with that is if you want an analog DC output, you put a digital to analog converter after it. Don't it?
There is Arduino reciprocal counters. We were playing with one on Saturday.
Okay.
We were measuring 2 hertz, and it was accurate to about 0.008 hertz.
Now I haven't done the numbers on this, but let's do the numbers. 6,000 RPM is not a bad sort of high speed for an engine. So it's no, that's it's 100 hertz, is it? Yeah, okay. What did you say? 2 hertz was 2 hertz was 2 hertz was accurate to how much?
We measured to 2.008 hertz, I think it was.
So you're getting say 1 part in 2,000. Yeah, okay.
We were using the oscillator out there,
Mhm.
the Tektronix,
Yeah.
and I brought in a frequency counter which I've got, which is actually a reciprocal counter,
Oh, okay.
and it was actually showing that at 2 hertz it was actually bloody stable.
Hmm.
And then
What I'm getting at is the resolution.
Mohan used a library out of the Teensy,
Yeah.
which has reciprocal counter function in it, so you can measure up to 1,000 hertz using reciprocal counter things.
So say that again. You can use.
There's
Oh.
a Teensy, Arduino frequency Teensy library, and you can measure up to 1,000 hertz. And with that,
With what sort of resolution?
Well, we actually changed the resolution from 2-digit to 3-digit. We got 2.008 hertz instead of 2.001 hertz. 2.001 hertz. So the Tektronix produced 2.001 hertz, and the Tinsy measured 2.008
Oh, okay.
hertz.
So it's out by 0.007.
Yep.
Yeah, okay.
And that's using reciprocal counter technique. And this was on a Uno board.
Mm-hmm.
It depends on the crystal on the Arduino.
Yeah, look.
I think it does, and that, in fact, probably what you're doing is measuring the error in the Arduino's crystal. Yeah.
Which is not a precision crystal anyway.
But it's
Pretty good.
Yes, yeah. So from what you're saying, it's looking like it's in the ballpark of doability with cheap components, because that tacho design, although it was a lot of components, there were no expensive components in it. There was a meter movement that was probably expensive, and people argue whether they prefer a digital display or an analog, and I can see arguments for both, strong arguments for both. And so, if this was being repeated, I think I would actually have both. It's much easier to get a feeling for what's going on with changes with an analog one, and the digital beats the hell out of analog for precision and accuracy. But yeah, so in terms of a frequency to voltage converter, I think there's a strong likelihood that a digital technique like you're talking about, the reciprocal counter, would be a nicer way to go. It would still need the pulse clean-up at the front. And also, we took a brave move. We're taking it off the high tension. It is much easier to do the pulse waveforms from the primary side. But there's probably a higher personnel risk with that one. And there are other ways, and I actually don't know with the modern vehicles, but I wouldn't be surprised with modern vehicles whether they've got a pulse output that's available somewhere that's
coming out of the ECU. It's just
exactly,
ECU function.
exactly. The ECU has to have it, so yeah. And so if that's accessible, that would be the way to go. Yeah. Yeah. So anyway, they're microcontrollers. Yeah, that's pretty much my report of some historical electronics. That's a little bit of it to the current day. Yeah, and involved a hell of a lot of work actually.
I've got a sort of an observation or a question there, John. I'm interested that you basically relied totally on frequency domain filtering. You didn't have any amplitude variability in any sort of form of picking up the peak and adjusting to the current peak levels or something like that. And given the huge range of signals that you're getting, it's fascinating that it could work with just frequency domain filtering.
Part of the reason for that is that the amplitude is about the amplitude of the overall signal is the same whether you're doing 600 revs per minute or 6,000. But I take your point, and I mean I'm not trying to describe my whole time there at GMH, but one of the things that I did down there, it worked out very, very well, was that I decided to take a modular approach because I realised that we're doing sort of one-offs and 10-offs and that sort of stuff a lot. And so these die-cast boxes became a standard module. And in many cases, if the thing was to be mains operated, one half of the box could be devoted to a 1 amp multi-tap transformer and power supply. So that gave us plus or minus 15 volts and plus 5 volts in a very standardised sort of way in that side. And then this side could say 2, perhaps even 3 boards stacked on top of each other. And so we ended up having a sort of a modular size of board that would sort of fit in there. And I had all sorts of designs, standard gain amplifier, inverting amplifiers, low-pass filters, high-pass filters, and I also had a slew rate limited one, which is getting close to what you're sort of saying, using nonlinear techniques. So there were occasions where I did use those sort of things, but point taken. And I'm not saying that this is necessarily the optimal way. I'm just sort of saying that there's a lot of work figuring out a whole lot of combinations.
That wasn't a critique as much as an observation.
Yes,
yes. Knowing nothing about it, my first sort of inclination would be, well, we've got to sort out the amplitudes of these signals and adapt to that. But effectively, what you're saying is you found that it was consistent enough, even with the sort of 30% variation depending on grounding, that you didn't really have to worry too much about that.
No. It's more a case of this. Oh, how the hell did that pulse get in there? Oh, it was points bounce or whatever it might be. Yes.
The whole thing is sort of, to me, it's part of that general thing that we used to do. Is understanding the process that you are trying to measure and observe,
yes,
and through careful study, work out what are the signatures here that are significant in the whole scheme of things. I mean, I've done.
Thank you, David. When I was driving here, and I forgot to say it at the start of the project, I got a thing sort of saying that. You really need to have a good idea of your goals. And if you're measuring something, you need to understand it.
You need to observe it and understand
yes.
it. And
yes.
I mean, I've got a few war stories in that department. One of the most interesting ones was, for some reason, we got involved in fluid level detection.
Mm-hmm.
And I can't even remember. And if you're doing, say, soil moisture or something like that, you have a couple of probes and you measure the resistance between them. If you know what you're doing, you don't use DC, you use AC, so you don't get electrolysis of electrodes.
Oh, okay. Yeah.
We had, I forget the exact context, something to do with the dairy or something, caused to start wanting to measure milk level detection. And so we stuck these electrodes in milk. We had just the simple square wave excitation. And I couldn't draw it on the board now, but I noticed that the signal coming out of the electrodes had this funny bounce back effect on it, which only occurred in milk. Now, I have no idea what was causing it, whether it was the fats, the liptides, or whatever the heck they call, that are saying, ouch, that hurt, and have some return. I mean, it's just this weird stuff that you get, and you need to really understand that.
Yes.
And maybe I may have left $1 million sitting there on the lab bench. I don't know. I've got this way of detecting if it's going to make good blue cheese or not. I don't know. Or whether it's got bugs in it.
Yeah.
It may have...
milk then.
Big pun?
Is that the A2 plus milk then?
That's the one. Yeah. Look, it may have been to do with... we've had a little bit of involvement with cleaning the sheep's teats to get rid of the bacteria. I forget what they call it offhand. If that gets into the milk, the farmer gets a lot less money for his milk. May have been something, it's so long ago I've forgotten, but just weird stuff can crop up. It really can.
Yeah.
And a lot of my career has been around that, characterizing the process, finding a signature, something you can work with, and then refining it, just like you've done there with the tachometer thing. Yeah.
Very good. Brian. He's getting the microphone.
One question and one observation. With your design, did you have any problems with magnetic interference? Being aluminium or die cast, it would stop the electric fields, but what about magnetic fields?
Look, I don't think so. Magnetic fields, by and large, tend to be high current ones. Look, the other... we ought to have a whole session on this, and I actually brought along a couple of my books. I've got a whole book on noise reduction techniques in electronic systems. And this is probably written by the world's expert, and another one. And so there are all sorts of things. Now, one of the things that comes out of that is, yes, you use die-cast boxes. Another thing, and particularly dealing with magnetic, is it's amazing how many magnetic things get fixed by putting the two conductors together and not separating them. And twisting is even better, for sure. Yeah. And so even the coaxial cable is not too bad with magnetic, because you've actually got the two conductors really close to each other, and so the magnetic field. So in the tachometer, no. There was one project that I did where probably magnetic ones came into it a bit. As I said, we had a noise and vibration laboratory called the chassis rolls, and there was another noise and vibration laboratory, and there was a fair distance between them. It would have been 50 metres. And the guys came to me one day and they said, look, we kind of like to have a hands-free way of communicating with each other, sort of, hey Fred, have you got the shifter down there? Right? Between the two chassis rolls, because the two laboratories, because they were two laboratories for the same team, and there were some times where they were actually conducting tests. And so I said, look, I reckon I could design you a system whereby there was microphone at this end and a loudspeaker there, and a microphone there and a loudspeaker there, and I reckon I can actually control it so it doesn't howl and feed back, because I've had a fair bit of experience in that sort of stuff. And to come to your question about magnetic, you almost always get hum on your grounds, and the grounds are separated by 50 metres, and most often those differences in potential are actually due to mains magnetic fields, and you've got a bloody big loop. In that case, I used a differential amplifier, so sort of the receiving end was measuring the difference between the active and and the ground lead that came up there. And so that was one way of putting up with and getting rid of magnetic fields, or the voltage resultant from the magnetic field. You look a bit dubious.
No,
Oh, okay.
understand.
Yeah, yeah.
The other question or comment really more was that back in my days when I was car racing, I know there was a lot of people where they had problems with bounce from the contacts, which would trigger and then misfire and all sorts of funny things.
Oh, it doesn't do great things for the engine either.
No, they used to fix it by just putting a bit of foam rubber between the contacts and some other suitable part of the distributor, so as it effectively increased the pressure and also damped out some of the oscillations in on the lobes.
Yeah.
And that's all they used to do, is put a bit of foam rubber. Didn't work, put more in.
I mean, one of the messages that come out of this sort of thing is horses for courses. You know, different things are applicable. So if you're into racing, you'll do all sorts of mods on your car. We wanted a tacho that could be just bolted onto a car and give the right reading. So we wouldn't have the time to fiddle around with the distributor, get the distributor performing better. But yeah. But yeah, so look, sometime we possibly ought to talk about some noise reduction techniques and stuff. There's a lot in it. You know, the business of whether you ground both ends or not and stuff like that. And one of the cases where you ground things, there are some cases where it's actually arguable you ground it, if you like, through a capacitor. By and large, one of the messages that I get from one of those books, if I understand it rightly, is, roughly speaking, people who have worked a lot in audio don't have ground loops, right? Single point grounds, no ground loops. Bullshit when you get to RF. You need to have grounded the shortest available as often and as wherever you can in RF. Now the stuff that we're dealing with is sort of both. And one of the messages I got from one of those books is, roughly speaking, 1 megahertz is sort of the dividing point, that below a megahertz you try and avoid ground loops and the like. Above about a megahertz you don't avoid them. And so that's what the capacitor does. The capacitor is there to sort of say, look, at high frequencies I'm going to ground you, and at low frequencies I'm going to leave you open. But yeah, there's a hell of a lot in that sort of stuff, and I won't say claim to say I understand it all, but I have understood a fair bit of it and had some contact with people who knew a lot about it. Yeah. Anyway, we probably ought to call it a night there.
Very interesting. Thank you, John.
That's okay.